Our rack system retrieves the wrong documents 40% of the time. Now, this is a problem that I hear every week in most of the teams that I actually work with. Same patterns. The team actually builds a rack pipeline. It works really well in testing environment, but it fails in the production environment. The problem is not in the vector database. It's not the embedding model, or it's not even the chunk size that they have selected for that given scenario. The problem is the architecture around it. See, what happens in most of the scenario over here is most of the teams, they actually build three elements, like they embed the documents, they store it in vector database, and the third step is they will perform the retrieve and generate. So that means they'll retrieve and they will pass it to the LLM. This works for demo, but it fails for production environment. See, if you consider creating the RAG architecture for the production environment, it not just have 3 layers, but we generally have 7 layers. We have 7 layers in the production rack system. We have document processing, chunking strategy, vector database, the permission filtering or permission filtering. Then we'll have the hybrid search, re-ranking, cost optimization. So these are all the 7 core elements that we would have in the production scenario. And then we'll have the LLM generation. So what happens is most teams, they actually build layer 1, 2, and 3. They wonder why the accuracy is just 60% and costs are getting exploded. Now, in this video, I'm going to show you the complete architecture, the real pattern, real cost numbers, and what actually works in the enterprise system. So let's start with the first mistake that most of the team make whenever they are working with the rack system. The question that most of them would ask over here is, okay, I'm building the vector database. Should I use Pinecone? Should I use VB8? Should I use Quadrant? Or should I use Chroma? Now, I'm going to say that's a wrong question. The reason is the right question is, what are my access pattern and what will be my scale requirement? Now, this is the s- clear decision framework that we actually use whenever we are doing the implementation for our client. So the scenario one is if it is in the POC or early stage, and if you are having less than 1 million vectors, then ChromaDB or Quadrant would be your first choice, which is a self-hosted one. Let me tell you why. First and foremost, it's free or low cost. It's easy to get started. You can just do the pip install or Docker run. You'll have the required things ready, and it has got good enough performance for this limited amount of vectors that we are talking about. And the best part is you can migrate later, but you need to avoid this whenever you are requiring the multi-tenancy, when you need production SLA, or when you have a distributed search. That's when you would avoid this Chroma DB or Quadrant. So if you look into the cost, it's somewhere between $0 to $50 per month. You'll have a second scenario that is production or mid-scale. Here we'll have, let's say, 1 to 10 million vectors. Here in this scenario, use Pinecone or VB8. Pinecone can be managed and VB8 can be self-hosted. So the reason, because this provides the production ready infrastructure. It provides you the better performance at scale, multi-tenancy support, monitoring and observability. Some of the advantage that you would get by using this Pinecone over here is, one is zero operation overhead. It is fully managed. It has got good performance, and mainly it has got very simple pricing. If you look into the disadvantage of this Pinecone over here, it can get expensive. Can the cost would vary between $70 to $300 per month depending on the vectors that you have got, and you have very less control over the infrastructure. On the other hand, if you look into the VV8, it's a self-hosted, so you'll have more control around it. It is better for complex filtering for your RAG-based application, and it supports hybrid search built-in. But the disadvantage over here is you have to manage the operation. That means the infrastructure. You need DevOps expertise to be able to manage this VV8. And the cost overall with this either Pinecone or BBATS, it is somewhere between 70 to 50, $500 per month, depending on the scale at which you are building the application. Then we have a scenario three that is for enterprise or large scale. This is for more than 10 million vectors. So here recommended to use either VB8, which is self-hosted, or Milvus, which is distributed. See, the reason this is recommended because we need distributed architecture, we need fine-grained control, we need to have cost optimization at scale because we are talking more than 10 million vectors, and we need to have the support of complex access pattern. And if you look into the advantage of Milvus, it is built for massive scale. It is distributed by design and it's an open source. Coming to the disadvantage of Milvus, it's little complex to operate. It requires significant DevOps. So overall, the if you look into this setup with this 10 million plus vectors, the cost is somewhere between 500 to 5K dollars per month. But at 100 million plus vectors, managed solution would actually cost you more than 10K. So that's something that you have to keep in mind if you're deciding it. So this is very important for you to remember. And hence, VB8 or Wilmus is actually recommended when you're operating at scale. So the real decision is always, it's not about which is best. It's always about where are you in your product life cycle? Are you in POC or are you in production? And what's your budget? Is $0 or is it $500 or $5,000? And what is your scale? Is it 1K or 100 million vectors? Do you have DevOps? That means, do you have the team to manage it? Or do you want to go to the managed or the self-hosted one? So my recommendation for most of the team, now this happens in most of my consulting calls as well. Start with ChromaDB, which is free and easy. Then move to the Pinecone when you hit the production. It could be managed and it's a reliable one. Then move to the self-hosted. It could be VB8 and when the cost matters, especially at the scale optimization. So my recommendation for the teams is don't think at the start. You can migrate to the vector database at a later point. And I've done it 3 times. But here's what you can't easily fix later. That is your chunking strategy. So your database is set. Next comes is the chunking strategy. Now, this is where most of the rack systems would fail. The common mistake is they make use of fixed chunk size without overlap, without context preservation. So as a result of this, see if we make use of the fixed chunk size, as a result of this, the context loss at boundaries, the related information is actually split across the chunk and it would result in poor retrieval accuracy. That's the problem that you would get by using this fixed chunks. So let's say I'll give you an example. If I have a fixed chunks, I might have a chunk one which says as Q3 revenue is $2.1 million up by 34%. And chunk two will have the details as growth driven by enterprise 67% increase. And chunk three will have the continuation that says as operating cost reduced by let's say 23%. Now, if the query is what drove the Q3 revenue growth, then the retrieved chunk will be chunk one, which will be about, let's say, revenue and growth. But chunk one doesn't have the answer. The answer would be in chunk two or chunk three. So in such scenario, the overlapping is the one that provides the better accuracy because it will help us in preserving the context at boundaries. The related concepts stay actually together and it will result in better retrieval accuracy. So just start by 20% overlap. That's a sweet spot that we have seen in most of the cases. And if you use the 50% chunk, if you use the 50% overlap, it would definitely result in high accuracy, but it will also incur you high cost. So my rule in most of the scenario is 20% overall for the general content and 50% overlap for dense technical document where context is highly critical because it's worth the cost. But remember, guys, this fixed chunks are still not the optimal one. The better one is the semantic searching or the semantic chunking. So instead of chunking by token, chunk by meaning. So there are various capabilities are available. If let's say if you're using the LangChain, you can make use of LangChain semantic chunker to perform the semantic chunking, which works really well. The way it works is it will embed each sentence and it will calculate the similarity between adjacent sentences, splits when the similarity drops below a certain threshold. So this would result in having a chunk that respect the natural semantic boundaries. So instead of splitting the mid paragraph, it splits after completing a topic or at natural transition point where the context actually shifts. So this would actually result in much higher accuracy, like I'll say 15 to 25% better retrieval in the overall testing that we have conducted. But remember, when you use this approach, there is a cost trade-off. So higher cost, more embeddings during the chunking. You are embedding every sentence to find the boundaries. And use this semantic searching when you are dealing with high value document, especially when you're dealing with legal, medical, and financial domain. That's when it's recommended to use it. And whenever the accuracy matters and when you have a budget for extra embeddings, go with this approach, but avoid it when you're dealing with large document corpus. Let's say if you have millions of documents, you don't want your cost to shoot up. And when you are in a cost constrained environment, or if you're dealing with simple documents such as blog post or marketing, then you won't require this high level of semantic searching. So the chunking strategy that I would generally prefer is 500 tokens per chunk, 100 tokens overlap, generally 20%, and semantic chunking for critical documents only. This is the recommended chunking strategy. So this will help us in balancing both accuracy and cost. Now, even with this perfect chunking, I've seen that the rack systems would fail because of missing the next layer, that is permission filtering. See, I've seen this happen repeatedly. The team builds RAG, it works, they deploy to the production. But then when the user A queries as, let's say, what exactly is my Q4 strategy? Okay, so what is our Q4 strategy? Then then what would happen over here is the system will retrieve the confidential executive memo, and that's a data which the user should not have the access to. And that's basically called as the data leakage. In demo, everyone has access to everything. As a developer, I'll have the access to all the details that has been shared to me, right? But in production, the permissions matter. But the problem over here is vector database don't know how to have the permission in your system, right? They'll happily retrieve whatever the user asks. It doesn't care. So the solution over here is the permission filtering layer. This is how the architecture would look like. We'll have a user query, we'll embed the query, we'll return the vector search output, and then we're gonna implement the permission filter. That means we keep only the accessible document. And then we re-rank the top 5 and we return to the LLM. And here when we talk about the implementation pattern, it's very simple. We generally prefer to use this metadata filtering. We store the permission as metadata in vector database. And by using this approach, the advantage that we would get over here is, so we'll be able to ensure that it's fast. It is especially while filtering in vector database, it scales well, and we don't require any additional service. Okay, that's the advantage that we would have with this preferred approach, that is metadata filtering. But coming to the disadvantage, metadata size limit, and we need to re-index on permission changes. So these are the few things that we have to be aware of. But we also have a second option as well, that is post retrieval filtering. Here, what you can do to get started over here is you just retrieve the documents and then perform the filtering. So in this scenario, this is a quick example as how it actually works. See, in this scenario, what you can do over here is the advantage over here is by using this post retrieval filtering, it is slower. So with this, you will have a flexible permission logic. It like whenever there's any permission update, it's much easier to do in this scenario. Okay, that's the advantage or the pros of this approach. It is flexible permission logic, easy permission update, and there's no metadata size limits. But when it comes to the disadvantage, it's slower. You might not get enough results after the filtering. So my recommendation is always start with this simple one, that is metadata filtering approach, that is option one, and then move to the post filtering option two. Okay, because you use this only when the permission rule gets complex or when the permission rules change frequently. That's when you would actually need it. Okay, that's the core idea here, team. Like, I'll give you a scenario. A client had 500K documents and different access levels, that is public, internal, confidential, executive. In that scenario, what we did was we just implemented the metadata on each vector, something like this. Like access level, we can have a access level, and we can have the department, we can have the allowed roles, and based on that, we implemented the metadata for each vector while doing the loading, and then we perform the filtering in the query time. That's the core idea. By doing this, this ensured that there is zero data leakage, especially, and we were able to ensure that zero data leakage over past 6 to 8 months so far now, and less than 50 milliseconds latency overhead, and it can even scale to 500K plus documents as well. Okay, so I want to tell you over here, and this is very important, permission filtering is not optional in production system. It's an essential one. It's ensure that you budget it from the day one. Don't add it later, because later becomes never. This is what I've seen in most of the organization, and then they had to redo the whole thing. Now, even with permission, in some cases, you'll still burn money. You have to be careful of that. Let's say if you don't optimize the cost. So let's take a look into the cost optimization. See, let me show you where the cost would actually come from the rack system. So let's take a look into the system stats. 100K documents, there are 5 pages per document on an average, and there are 500K total pages, and you have to perform, let's say, embed, store, and query. Okay, let's take a look into the cost that we have got. Okay, let's start with the embedding cost. If you take a look into this embedding cost, okay, so let's start with the embedding cost. Let's say if we are using the OpenAI embedding 3 large, okay, let's take if you consider that example, the cost is $0.13 per 1 million token. The average document is, let's say, 2000 tokens, and we'll be dealing with 1 billion tokens, and the total embedding cost will be $130 one time. Like, that would be the embedding cost. But wait, we have also said that there's 20% overlapping of chunking, right? So add 20% more, that would be $156. But with semantic chunking, let's say I'm going to embed every sentence first and do it. If you use that approach, consider it as double for boundariness. So if you use that approach, the cost would come to $260. Now, let's take a look into the vector storage cost. Like, I've just considered the Pinecone as a database as an example for pricing. So $0.096 per 1 million vectors per month. If I assume that for 500K pages, like I'll say 600K chunks with overlap, this would result in close to 600K chunks. And the total storage cost would come to close to $60 per month. Now let's take a look into the query cost. Okay. So the real usage, let's say there is a 10K queries per day. Okay. Let's say that is one of the system stats that we already have. Now in such scenario, each query retrieves top 5 chunks. Okay, each query retrieves a top 5 chunk, and 10K into 5 is 50K vector search per day. Like that's what we can easily consider. And if you take a look into the Pinecone query pricing, which is generally included in our pod pricing, but LLM cost for retrieved context is also need to be considered. Let's say if you retrieve 5 chunks, there will be 500 tokens per chunk and 2500 tokens per context. So 10K queries by 2500 tokens, it is 25 million tokens per day. And I've just considered very old model. Now you can use a latest model as well for the pricing. You just have to change it in the calculation. I'm just showing you because this is what I've seen in my earlier application that we have built. So I've just considered GPT-4 Turbo as an example. Let's say $10 per 1 million token. So the LLM cost per day is $250 per day, which is $7,500 per month. So if you take a look into the total cost, $58 for vector storage, LLM cost is 7,500 and total is 7,558 per month. The one-time cost, depending on the embedding, this would be the one-time cost of embedding storage. The real shock over here is the vector DB. If you take a look at it, it's just 58%, which is 1% of your entire spending. The LLM cost is the most expensive part, which I've seen most of the teams who are building it are actually missing. So with this, how can you optimize the cost? See, the strategy number one for your scenario over here is start with like reduce the retrieve chunks. Instead of top 5, retrieve top 3 if you're serious about cost saving. That would result in, let's say, before it is 2500 tokens per query, it would be 1500 tokens per query. You are going to save $3,000 per month. Trade off. If you use a strategy, there will be slightly lower accuracy, but more in most of the scenarios, it's often negligible. Second, use the hybrid search and re-ranking. Don't send all the 5 chunks, or just go ahead and re-rank them first. Like say retrieve 10 candidates, re-rank to top 3 and then send to the LLM. Apply the re-ranking. So here for re-ranking, you can make use of, let's say, Cohere re-rank API. That's going to cost just $1 per 1K searches, which is very cheap. Or you can also make use of local BERT model, which is free, which will add a latency overhead, but it is less than 100 milliseconds. That's what we have seen. Then with re-ranking, as I mentioned, do this 10 candidates, like retrieve 10 candidates. It can be a broader recall, then re-rank to top 3, which could be a precision one, then send the top 3 to the LLM. So this would result in much better accuracy. 10 candidates is the better recall. It would result in lower cost because you're using 3 chunks to the LLM instead of, let's say, 5. So it would result in net savings of 2,700 per month. So there is a little cost overhead with Cohere because of re-ranking, but that should be okay. The strategy number 3 is caching the embeddings. Smaller chunks for storage and larger chunks for LLM. So here in this scenario, okay, store the smaller chunks in vector database and retrieve the parent document sections for the LLM context. So that is the strategy number 3. I think I've not mentioned it here. I've noted in my notes. Okay, let me mention it. Let me speak and then I'll come to this cache embedding. So there's one more strategy that you can do it. The other strategy is use the smaller chunks for storage and larger context for the LLM. That means use whatever the small chunks that you have got in your vector database and pull the full blown document from the document storage for the LLM context. So this would result in b- like better retrieval accuracy. You'll be able to get the parent sections, and it would also result in duplication. It won't be much better. I'll say it's not in the cost optimization one. I think that's the reason that I've not added for this diagram, but that's also another approach that you can consider. And the other strategy that you can use it is caching the embeddings. Like if same documents are queried often, cache the embeddings. So by doing this, this would actually result in 30, like for example, if 30 to 50% of your queries are similar, cache the embeddings. Then if there is a cache hit, there is no embedding cost. The embedding cost, let's say if it is $0.001 per query, at 10K queries per day, you'll be able to save $150 per month. So it's small, but it would definitely add up. So my production cost optimization stack would be something like this. Okay. So my production stack for this cost optimization would be something like this. So retrieve the top 10 documents, perform the hybrid search, re-rank to 3 using the cohere, then send these 3 chunks to the LLM, which would be just, let's say, 1,500 tokens, and cache the common queries. These are the 4 things that I would mention for the cost optimization stack whenever we are building the production grade RAG. So the rule is always simple. Optimize the LLM context cost, not your vector database cost. Vector database is less than 1% of your total cost. The LLM is the 99%. Now, let me show you what RAG actually look like, the production RAG. We'll have a layer 1, which is document processing. This is where you parse PDF, Word document. You will preserve the structure. You will handle the images if with the help of OCR if needed. Then you'll have a chunking strategy with 20% overlap, 500 tokens per chunk, semantic search, semantic chunking for critical documents. Then for embedding and storage, let's say use the OpenAI model, store it in Pinecone or VV8. Then query processing, embed the query, hybrid search with vector and keyword, and retrieve the top 10. Then apply the permission filtering, metadata based filtering, and keep only the accessible documents. Apply the re-ranking, re-rank the top 10, like from re-rank from top 10 to top 3, use the cohere or local model and get the precision boost. And finally, send it to the LLM. Assemble the context, that is 3 chunks, generate the response, and cite the resources. So that should be the data flow, guys. So most teams build only layer 2, 3, and 7, but in production, all 7 layers. This would result in more accuracy, zero data leakage, and lesser cost. That's how you would build the production rack. This is the complete architecture that you can follow. So this is the tech stack. I've shared all these resources, including the diagram that I'm sharing to you right now. So I'm sharing everything into our community, our private community. Go ahead and join and access these resources. I keep on sharing it in case if you're building the production ready rack system. Now, if this is the level that you want to operate at in your Agentic AI career, I also run a live instructor-led cohort where I teach live from scratch to help you build this production-ready agent. So if you're up for the game, sign up for it. If not, just stay connected, guys. I look forward to helping you in your Agentic AI journey. Subscribe to our channel, and I'll see you next time.